proof with modular arithmetic or spotting the pattern. There's a lot to get stuck into.
Tom, you've been using this for sort of admissions purposes. How do people normally go with it? What kind of percentage of people crack it, and how many get completely flummoxed?
It's interesting. Some people go down the route of actually trying to do the algebra. So they say I have a square that's x by x, I have a rectangle with set length y, and they sort of construct all kinds of complicated equations. And you don't really get anywhere with that, unfortunately. So lots of people go down that route and get very lost. And then my job is to kind of steer them back, say, well, let's draw some pictures. And then you have the other people who just start to draw pictures. And then, as I mentioned at the beginning, once you've figured out just drawing some pictures, you can then either say, like, try and do it case by case. But the problem with doing that is you would try 3 and 4, and as we've seen, they're not possible. So lots of people spend a lot of time trying to do 3 and 4. So that's why I suggested my way of approaching any problem like this is try and find as many correct things as possible and use them as like your footholds on the ladder, and then build up other ones from there. So I've definitely had students get all the way through. I think I'm trying to remember, maybe once or twice has somebody figured out the n equals 7 case, because that's quite tricky. There's a lot you really need to, that took me a while to sit down and keep drawing rectangles until I got that one to work. But the good students, the good candidates will be able to get through and spot the pattern with the adding of 3. And that's the key thing, really, I think, in terms of the maths behind this, is spotting that pattern, and that you can use those lower cases to generate all the higher ones.
I'll tell you why I probably wouldn't get into Oxford then. My instinct was that you were going to use area.
So that's another way of looking at it, actually. You can get somewhere with the area, but again, you kind of have to be algebraic, because you say, you've got x by x squared, you've got a rectangle which is y and 2y, so its area is 2y squared. And so you can, but the problem is, because you're allowed to have an unknown number of an unknown size of rectangles, there's too many variables. So whilst I think you could use that to perhaps show some of these work, or that 3 or 4 don't work, I think you would struggle going down that route just because there's just too many variables. So I think here it really does help to just get stuck in and just draw pictures, which is, again, why I like it so much, because you don't need much mathematical background or knowledge. Hopefully anyone watching this can draw rectangles and squares and have a bit of fun with trying to figure out what's happening. And then this is just going to carry on. So you can look back through our lists as well and see, we had 14, 17, and you could tick them off. But if you spot that because we had these 3 numbers in a row, and we had this n+3 rule, we're actually going to get all of the other numbers. And what's really happening there is all to do with remainders, or modular arithmetic. Because the way you can think about this is, if I take any number in my list, absolutely any integer, if I divide that number by 3, there are 3 possible things that can happen. It can either be perfectly divisible by 3, remainder 0. It can give me remainder 1, or it can give me remainder 2. Now, if there was remainder 3, it would actually be, you'd add an extra 1 to the numbers of 3s that went into it, and you'd be back at remainder 0. And similarly for 4, 5. So these are the only 3 possible remainders when you divide by 3. So this would be 0 mod 3, 1 mod 3, 2 mod 3. But we don't have to use the fancy language, it's just remainders. So if we now look at our numbers, we can see that 8 here is remainder 2. So if we know that it's true, so this one corresponds to 8. So we know that it's true for this, then I can just keep adding 3, following my n+3 rule. If I know it's true for this one, remainder 2, it's true for every other number, remainder 2. Because every time I add 3, the remainder doesn't change. And then similarly for remainder 1, that's going to correspond to the number 10 up here. And then remainder 0, this corresponds to the number 9. So because we have these 3 in a row, they fit this modular arithmetic or remainder style argument, we now actually sort of have a proof that we can get every other possible number.
I thought you'd already proved it when you did that to build those 3, and you knew from that you could build the next 3 and the next 3. It felt to me like you'd already proven it.
Yes, so I agree. So I think you could just Another way to think about it would be to say, because we had these three, we can, and n plus 3, we can then like iterate, repeat the same process. That would be also, I think, a valid way to prove it. Maybe I just wanted to talk about modular arithmetic because it's a nice way of considering larger numbers.